Most clustering algorithms open with an awkward question. How many clusters are there? Pick the wrong number, and everything downstream is quietly off. But what if you never had a guess? What if the algorithm could just look at your data, find the crowded regions on its own, and set aside the stray points that belong to nothing? That is exactly the promise of Dbscan, and it pulls it off with only 2 simple settings and 1 intuitive idea about density. Let's dig in. First, let's see why Dbscan thinks so differently from a usual approach. Think about how the classic k-means method works. It demands a number up front. You tell it there are, say, 3 clusters, and it dutifully carves the data into exactly 3 round blobs. Every single point gets forced into some group, even the obvious outliers, and if the true shapes are rings or curves, k-means gets them wrong. Dbscan flips the whole thing around. It never asks how many clusters exist. Instead, it hunts for regions where points are packed tightly together, links those dense regions into clusters of any shape they happen to form, and labels the lonely, sparse points as noise. No number to guess, any shape allowed, and outliers handled for free rather than shoved into the nearest crowd. So how does Dbscan actually grow a cluster from scratch? Follow the loop 1 step at a time. Start by grabbing any point you haven't visited yet. It could be anything, a point buried in the middle of a crowd or one stranded off on its own. It is simply going to ask one honest question. How crowded is its neighborhood? Now draw a small circle of radius epsilon around that point and count how many neighbors fall inside. Epsilon is your first setting, the reach of the neighborhood, and this count decides whether the point sits inside a dense region or out in the sparse wilderness. If that neighbor count meets your minimum points threshold, congratulations, this is a core point, and it becomes the seed of a brand new cluster. If it falls short, the point is set aside for now, either a border point clinging to some cluster's edge or noise that belongs to nothing at all. From that core point, the cluster grows outward. Every dense neighbor gets pulled in, and if any of them is also a core point, its neighbors join too. So the cluster keeps chaining through connected dense points until it reaches the sparse boundary and stops. Then you move to the next unvisited point and repeat, until every point is either inside a cluster or marked as noise. Strip it all down, and 3 ideas make Dbscan what it is. Clusters are simply dense regions. A group is any set of points packed closely enough that each core point has enough neighbors within epsilon. Density defines membership. So the algorithm follows the natural crowds already present in your data rather than imposing a rigid, predetermined shape on top of them. It discovers arbitrary shapes with no number of clusters required. Because clusters grow by chaining together neighboring dense points, they can bend into rings, ribbons, and curves that round blob methods like k-means could never capture, and you never once have to declare how many groups to expect. It labels the leftovers as noise. Points that never land in any dense region are explicitly flagged as outliers instead of being forced into the nearest group. That built-in anomaly detection is exactly why Dbscan shines on spatial data, on messy real-world measurements, and on any dataset riddled with irregular structure. All right, let's lock in what matters. Dbscan finds clusters as dense regions of points separated by sparser gaps, using just 2 settings, a radius epsilon and a minimum number of neighbors. Points with enough close neighbors become core points that chain into clusters. Edge points become borders, and everything left over gets labeled as noise. Its big advantage over k-means. It needs no number of clusters up front, discovers clusters of any shape, and flags outliers instead of forcing every point into a group. Its catch is uneven density. Since 1 epsilon can't fit clusters of very different tightness. And choosing that epsilon well is the real practical skill. Want more machine learning ideas made this clear? Unpacking exactly this kind of thing is what we do over at Standarity.com. Come join us.